Hello, this is Haidong from Tencent AI Lab. Here I present the work of our team. TVM enable real-time character control for mobile games. So the project is about mobile game and real-time character control, and it requires real-time computation. So we use TVM to accelerate the algorithms. This talk has four parts. Firstly, I will introduce the background and then TVM enable methods, performance analysis, and the lessons we learned from this project. Okay, so firstly, the background. It is game character control. In this animation, the so-called game character control is the point of the underlying underground, the point and the arrows. So for real-time character control, the algorithm predicts the anchor point of the game character in the next frame, so that the game core can render according to the points and arrows. So the entire algorithm is embedded in the mobile games for real-time computation. So this is not a cloud computing scenario. So the latency here has a very high requirement. If we have 8 characters in the game scene, we want the inference latency to be within 2 milliseconds. This is a very high requirement. And finally, the entire project will be deployed on Android and iOS on cell phones, and will be developed on macOS and Windows platforms. So cross-platform and is very important feature for us. About the algorithm is phase function neural network, which is called PFNN for short. So the neural network architecture is a very simple 4-layer fully connected. It's a very simple 4-layer fully connected neural network. The weight matrices are interpolated by a phase function. The phase function is conducted on the weight matrix and accepts a phase value as its input. The phase value corresponds to the game character status. For example, when the character steps by the left foot, it has a phase value. When it on the right foot, it has another phase value. So the phase value just change, and the weight matrix will be interpolated to the right one. Okay, so this is a very special case. Compared with typical neural network layers, the weight matrix is just static, but for PFNN, the weight matrices are dynamic. Okay, so the problem arises when there are multiple characters in the game scene. So here we have n characters, and at any time point, they will not behave in the same status. So their phase values are different. Therefore, their interpolated weight matrices are different. So we cannot efficiently compute them in a batch. So our straightforward solution to this is that to fuse the interpolation function with matrix multiplication. Okay, so here so if we can successfully fuse the operators, we don't need the interpolated weights. In the world, we want to get rid of this interpolated weights. So this is feasible because that the interpolation function itself is element-wise, which means that the phase function does not need a row or a column in the input matrix in order to compute a result. So it is fusible. Okay, let's take a closer look at the pseudocode. The phase function loop is here, We don't need to dive into the details. Okay, and here is the vector matrix multiplication loop, which computes the fully connected layer. So the fuse operator itself only fuse the two loops together and change the loop orders. We have two observations here. Firstly, the fuse operator as the fuse operator reduces the interpolation matrix, which is RC, into a local variable t. Therefore, we don't need to store them in separate matrices. And the second observation is that the loop order of the fuse operator here, look at here, it is identical with the matrix multiplication, okay, of shape C by K and K by N, where C is the checked number, C is the checked number, and K is the feature vector length. Okay, so therefore we can borrow the optimization techniques for the fuse operator in order to generate some really high performance solutions. Okay, let's look at our TVM enabled approaches. We have used three different approaches in order to leverage TVM. The first is TVM with manual scheduler. Okay, so we first define the tensor expressions, the algorithm, and the write schedulers and tune manually. Everything is done manually. And finally, automatic code generation and deployment. So with this approach, TVM is more like a cross-platform code generator. And here, if we want to write an efficient scheduler, it requires high HPC knowledge, but we are cool about it. We have very strong HPC background. Okay, the second approach is auto TVM with external kernels. The so-called external kernels are handwritten, and we have already composed some of the very efficient inner kernels for every hardware, which covers the desktop CPUs and the mobile CPUs. And we have to compose scheduler templates for auto TVM to tune. So we first define the tensor expressions and prepare the kernels and the auto TVM templates and let the entire system to tune the parameters. It might run for hours or days. And finally, deployment. Okay, so this approach, the motivation of this approach is to achieve best performance. If you really want to, if you really care about the last ounce of performance, this is the way to go. The last approach is answer. It is an end-to-end approach. So we only define the tensor expressions and let answer to automatically generate and tune the schedulers and automatically deployment onto the target. Okay, so the good thing about answer is that its search time is very short, about 1 or 2 hours, and the result is very desirable. We'll see later. Okay, so about deployment, let's see our workflow. So first, we need to pack the TVM runtime into the game core. So TVM has a very simple packed runtime, which is easy to integrate. We just copy this source code into the game core project folder and compile. Everything works perfectly. And for the kernels and the runtime library, we follow this offline tuning pipeline. So the performance tuning pipeline here, we define the algorithm, we write the scheduler or auto-generated, and generate the respective optimized library which contains the kernel functions for the algorithm for PFNN. So if we generate shared library, it can be put in the game resource and let the runtime to dynamically to load them as needed. And if we are using static libraries, which is called system library in TVM's term. Okay, so the static libraries need to be compiled alongside with the game core. Okay, so this is our deployment workflow. Let's see the performance analysis. Our baseline is agent, which is a widely used BLAS library. We can see that the green bar here is for agent. We can see that with 8 characters, the performance is about 3 or 4 times slower than the than we have 1 characters here. So now the performance is not acceptable for our business partners. So this is mainly due to that agent cannot fuse the interpolation and fully connected layer operators. So fusion makes a big difference here. Even if agent can be much faster than this performance, let's say 4 times faster, it is still not very desirable. Okay, so with any, so the claim here is that with any traditional inference neural network inference library or BLAS library, we cannot meet our goal. Okay, so our TVM baseline, which is the hunt schedulers, okay, they are the orange bars here, and this. Okay, we can see that if even we can see that it meets our goal, right? So the best part about this hunt scheduler is that if you know about a lot about HPC, you can develop them in a really quick cycle. So I have developed in 2 hours for 2 kind of processors. They are similar, right? And the parameters are just roughly tuned, and the outcome is desirable. It is decent. This is very decent performance. We are satisfied. Okay, for the next approach, it is auto TVM tuning handwritten in the kernels. So for this approach, it achieved extremely high performance, which is 30% faster than our hand-tuned schedulers. So below is the roofline chart. The roofline chart shows the roofline performance that you can achieve by the hardware. So when there are multiple characters, so we have more computation over memory access. So the arithmetic intensity is higher. And when we have 8 characters, the performance is more likely to be bound by computation. And we can see that with the auto TVM approach here, some layer can almost achieve the compute bound of the hardware. So this is very desirable performance. And with answer, consider the fact that it is an end-to-end approach, and it converges quite fast, only 2 hours, and it consumes these few human efforts. I only define the tensor expressions and nothing else. So the performance here, it beat our hand-tuned schedulers and almost add shooter to our bus to our bus solution. Yeah. So answer is very desirable. Okay, lastly, I will talk about the lessons learned. What went right? So about performance, we have shown in the last we have already shown that the performance is very desirable and met our business goal. The operator fusion is makes a big difference. Many people argue that operator fusion isn't that important. However, in this case, operator fusion is very important, and the TVM is really good at it. And the second thing, for roughly tuned schedulers, we are satisfied. And the auto TVM can almost achieve the hardware peak. This is very amazing. And also, answer achieve very good performance. We will apply answer in more widely in our business. About usability, the pack runtime is easy to integrate and easy to customize, and TVM scripts are written in Python, so this is very easy to maintain. If we need some new platforms, we just make some new export primitives. So cross platform, it is a very desirable feature. And what went wrong? The bad things are here. So firstly, we have observed that RVM has some corner cases that prevent TVM to achieve higher performance. And the second thing is that sometimes we really want our handwritten inner kernels and the schedulers can cooperate better. We have already noticed the newly released Tensor RR, and we think it is magic, and we want to see more documents, and we want to contribute more examples. And the third bad thing is that auto TVM cannot converge stably. That means that it means that we have to make lots of trials to achieve best performance. In our case, we spent about 3 weeks to achieve such good performance. About usability, the first thing is that static library is it is very useful for game development. So we want some official support. So in current version, static library needs some hack to work. And the second thing, we don't really understand why TVM cannot be installed through PEEP or Anaconda. Sometimes we need to reproduce our scripts on other machines and for other people. We don't want to teach everyone in our team to learn to build an entire TVM on their own computer. So we really want TVM that can be installed through PEEP or Anaconda or some other forms. Okay, the last thing about usability is that the TVM always assumes static shapes. So, however, in our case, the mobile games, the game character number just changes dynamically. So in this business, we have to generate the library for all possible character numbers. So if TVM has a better support for dynamic shape, things will be much easier. Okay, so that's all. Thank you.